It's time to start. So let's start. Good morning, everybody. Welcome to a hopefully exciting, I know it will be, morning of chemistry, Chem 1211, with your host, me, Dr. White. Hi, everybody. And I get to be a wild and crazy guy this morning. I should warn you later today, the lab will be you'll be working with, first of all, I wrote it myself. And at COD, I bring the chemicals in. That's the story I don't want to talk about. But I bring in some real dangerous chemicals like vinegar, tomato sauce, or paste. That's even more dangerous. Mustard and ketchup, the dangerous stuff. All right, here's the game plan today. First of all, I'm going to go through the problem set for chapter 15, equilibrium. And I know a lot of you are still sort of, what would be a nice way, finding your way with Le Chatelier's principle. So we'll practice that again today. Speaking about Le Chatelier's principle, the lab due today, if you're still having problem with it, I'll stick around after today's lab and answer any questions. I had a whole group of very nice people stop by my office hour last night with questions about that. And guess what? I answered them because all questions are good questions. All right, let's get going. Thumbs up, people. You see chapter 15 practice problems. Thank you. Let me just check one thing. Okay. All right. These are all things you should practice for test number 4. Wow. It's already test number 4. Boy, this semester's just time flies when you're having fun with chemistry and Dr. White. All right. First one. Name one of the key factors in the collision theory of reactions that is needed in order for a chemical reaction to occur. You only have to name one, but I named all 3. Reactant molecules must collide. That's why it's called the collision theory. Next, when they collide, let you see that collisions must have enough energy to make a reaction. And finally, molecules have to have the proper orientation when they collide. Number 2, what is the activation energy? That's the amount of energy needed to make a reaction when reactants collide. And how do you make a reaction go faster? Well, you can add more reactants concentration. You can increase the reaction temperature. And I just thought of something else I could put here, or you could put here. You can add a catalyst. Those would all be proper. Next, we have an energy diagram. And you should know how to draw energy diagrams. And here's the equilibrium we happen to have. And it doesn't have to be an equilibrium, but in this case, it is an equilibrium. And here you take nitrogen, hydrogen, reacted with to make ammonia plus heat. And 2 German chemists came up with a catalyst system for this to make this work in chemical plants, Haber and Bosch. And quick story, I'll do the energy diagram, then I'll give you a little quick story. All right, remember energy diagram, the y-axis is energy, the x-axis is time. The amount of energy on the reactant side equals the total energy on the product side. When you do chemistry, a chemical reaction, you never create or destroy energy. So arbitrarily, I'll say the amount of energy on this side, the reactants, nitrogen, hydrogen, is this amount. And then you go over a hill and down the hill to grandmother's house. You go, no, anyways. Now, On this side, you have ammonia and heat. Now the heat is lost, it goes off. So does ammonia have more or less or the same energy as nitrogen and hydrogen? And the answer is less. Why? Because the total amount of energy equals the energy on this side, and some on the product side is lost as heat, which is why ammonia is lower. So for an exothermic reaction, which this, ooh, that would be a good test question. What kind of reaction is this? When you give off heat, exothermic. How do you know you give it off? It's on the right side. I'm going to assume you all know your right from left. If not, come to my office hours and I'll help you out. But the other thing is, which I didn't write on this question, but I could have, also include the activation energy. And the activation energy is where you start to the top of the hill. And it's abbreviated by E subscript ACT. Now here I have another reaction, and again, draw the energy diagram, show activation energy, again on the y-axis energy, on the z-axis, and I see a question. Biljana, no, it would not be. I hope by now you people have learned Dr. White's not sitting there and grading tests. Ooh, how can I take points off? No, I look, is that right? And if you put the coefficients down, and guess what? You're not the first one, and you won't be the last one to do that. It's okay, as long as you have the graphs right, and I know which is a product, which is the reactants. And trust me, over the years, oh yeah, I have been teaching it over the years. I've seen many students do that and some don't. It does either way. Did I tell you I'm that close to the person grading the test? Me. And now you've got witnesses. I've said that. You're welcome. All right, let's get back. And remember, all questions are good questions. Thank you for your question. So if you were to put 2H2O, that's okay. Now let's look at this reaction. Water plus heat gives oxygen, hydrogen and oxygen. Now, is this an endothermic or exothermic reaction? I'm going to give you 8.2 seconds while I have some tea. And the answer is it's an endothermic reaction. Thank you, Anne. And how do you know that? Because you have to add heat. When heat is on the left side, it's endothermic. You have to add. When heat is on the right side, it's exothermic. It's given off. Now, remember, the amount of energy on the reactant side is equal to the amount of energy on the product side. You do not destroy or create energy in a chemical reaction. But here, water, does it have less energy or more than hydrogen and oxygen? Well, the total energy here is water plus heat, but you have to add the heat. So therefore, in an endothermic reaction, the reactants are lower energy, here's the energy, than the products, because you're adding energy to this to get to there. And then you go over the hill. That's not my best hill, but it works. Over the hill and down the hill, the grandmother's house, you know, to the products you go. And the activation energy, which you should know from where you start to the top of the hill. Now, one question I should have for you. Ooh, Dr. White's going to make you work this morning. I'm going to make you use your noodle up here. How does a catalyst work? Remember, I said how, not what is a catalyst, but how does a catalyst work? Oh, I just did the thing from Dances with Wolves. Remember when she goes like this? Never mind. Dr. White's mind is becoming a Star Trek mind. It's going where no other mind has gone before. Time's up. How does the catalyst work? No, it doesn't speed up the reaction. When I ask how, that's what it does. How does the catalyst work? A catalyst lowers the activation energy. So what it does is lowers that hill and it makes it easier to go over. And that's how a catalyst works. Now, and remember, look and read questions. If I ask what is a catalyst, then the answer is it's something that speeds up the reaction rate. If I ask how does a catalyst work, the answer is a catalyst works by lowering the activation energy. Now, something I don't have open, and I better open up. And if you look at important information on test number 4, which is on the screen, I don't give you anything about how to do the following thing. So this is one of those things I'm going to ask you to memorize. And the question is, write the equilibrium constant for this reaction. And let's do real quick. Let me open that up. Thumbs up, people. Do you see for the following reaction on your screen? Thank you. All right. Now, how do you write an equilibrium constant? It's the concentrations of each product to the power of the coefficient of that product times each other divided by the concentration of each reactant to the power of that reactant. And it's times. Students want to put a plus here because they see this, and that's wrong. It even says it on your screen. It's wrong. Uh-oh, bad humor slipped out. So let's go back to this problem. And how do we do that? We have the power of each concentration of each product on top to the coefficient. Notice here it's 4, that's why it's to the 4th power. When there's no coefficient, it's 1. And notice here it's the squared power. So why don't you write the coefficient? Let me move this. I make you work today. Can everybody see the bottom of the screen? 2FeBr equilibrium 2 FeBr2 plus bromine. Can you see that okay? At the very bottom of the screen. Can you see it, Biljana? All right. Hold on. Now can you see it? Good. Write the equilibrium constant for that. Go. I like that. Go. Get moving. Start working. Be quiet, Dr. White.
Dr. White, at the end of that, is it BR2?
Yes.
Okay,
Hold on.
thank you.
It's Dr. White. Time to take penmanship lessons again. Is that better? And all questions are good questions, and that's a pretty good one. What the heck did you write there? My first grade teacher would be upset with me now. You know how to write your numbers better. Back then I wasn't Dr. White. But I was getting into chemistry back then even. The mad scientist. And when you're done, give me a thumbs up. And those of you who don't have your webcam on, please turn it on and you can give me a thumbs up with an emoji. But remember, I'm renaming emoji Symboli. All right, I think everybody's done. Let's do this. First of all, on top goes the concentration of each product. And it's to the power of the coefficient. That's 2, bromine is 1, so you don't have to put anything. And on the bottom, you put the concentration, and by doing this, this means moles per 1 liter or 1,000, and that's what I mean by concentration. And here we have the ferric bromide, and it's to the power of 2 because the coefficient is 2. Now, number 7, predict the relative amounts of reactants and products for the following equilibrium where you're given the equilibrium constant. And let me remind you, when KEQ is greater than 1, much greater than 1, the amount of products is greater than reactants. Because remember, roughly KEQ is something to do with concentration of products divided by concentration reactants. In a very coarse way, this is one way of thinking of it. And therefore, if this number is greater than 1, the top has to be greater than the bottom. Now, if KEQ is much less than 1, then the reactants concentration will be greater than the products. And again, look over here. If the reactants are now larger than the products, this is going to be a very tiny number. Now, if we look over here, which is 2.0 times 10 to the 4th, that's much greater than 1. Therefore, by the way, 3 dots like this in math and logic means therefore. Oh, I'm teaching you so much good stuff today. It's amazing, isn't it? For those of you who never saw that. All right, so let's do another one. Here, there's a minus sign, The K equilibrium is 3.2 times 10 to the minus 34th for this reaction, which means it's much less than 1 and reactants are greater than products. All right, can everybody see D at the bottom right here? Can you see that? And in case you can't see it, you predict which is greater. What's the relative amount of products to reactants? Your turn. Told you I'm going to work your brain hard this morning. And for those of you who can, turn on your webcam, please. That makes Dr. White so happy. Don't you want me happy? Remember, Dr. White knows chemical warfare. Actually, I do. Ooh, I shouldn't have let that out. All right, when you're, oh, I haven't used this today, so. Ta-da! Oh, it looks like everybody's done, so let me get to work. The question is, predict the relative amount of reactant or reactants or end products for this reaction. Notice 1.0 times 10 to the minus 25th. When this is minus, it's going to be much less than 1. When it's positive, it's much greater than 1. It's much less than 1, and therefore, 3 dots, therefore, reactants will be greater concentration than products. All right. Now for the part you've all had some problems with, or maybe not all of you, some of you, with Chatelier's principle. How do you like my Northside Chicago French accent? But anyways, and by the way, if you haven't figured it out, I am butchering that name big time. But that's my accent. All right, for the following reaction, notice you're given an equilibrium reaction. And hint, what happens to oxygen concentration and chlorine concentration, Cl2, if you add more water? Now, let's go through the mindset for this. At equilibrium, there's a certain amount of chlorine, water, HCl, and oxygen. If I add more water, the equilibrium goes, oh no, we have too much water. What do? We got to get rid of some of that excess water. So we're equal to, again, the equilibrium constant. You didn't know molecules could talk to each other. They can. No, not really, but it sounds good. And how do you get rid of excess anything? You react it with something. When it reacts, it's consumed. And when it is consumed, like my French silk pie that I haven't bought, Dr. White's been good. He hasn't run out and bought one. And you have less. So how do you get rid of excess water? It reacts with chlorine to make more HCl and oxygen. Well, if it reacts with chlorine, chlorine is going to be consumed. Therefore, you'll have less. It decreases. Now, if chlorine and oxygen are reacting to get rid of the excess water, they go this way to make more HCl and oxygen. And therefore, if you're making more of something, you'll have more and the amount increases. And that's how you do it. All right, can everybody see 9? And let's do B. What happens to the concentration of NO2 in water, nitrous oxide in water, if you add more ammonia, NH3? Your turn. Am I being nice or what? I'm letting you have all this fun this morning. Have you noticed if I say the word fun enough times, you might believe me? Actually, it is fun, at least for me. Hopefully for you too. And when you're done, do a thumbs up. I'll go to the non-webcam people. When you're done, give me a thumbs up symbolically. Remember, I'm not using emoji anymore. I'm creating my own word.
Dr. White, I have a quick question.
I do slow questions too.
This could be it. On with the coefficients, when you're asking these questions, like what happens to that NO2 and the H2O if you add more H2,
Yep.
the coefficients from the original like equation or reaction
Like
are
number
gone.
9, the 2, the 7, the 2, the 4.
Right. So do we not include the coefficients in our response because we include them if we write that equilibrium equation?
Right. But what I'm looking for is just a rough approximation. What happens to the concentration? Therefore, and that's a very good question. Thank you for asking it. You ignore the coefficients for Le Chatelier's principle. We're just looking at it at a very coarse level. What happens approximately to the concentrations of different reactants? And in real life, it really happens.
Okay, so we use them for the equilibrium equation.
Constant. Now, can you keep a secret? Dr. White doesn't believe in doing the following because I've never done it. Some chemistry instructors, since this is hidden in the video, nobody will ever see it except you people, have questions where if the molar concentration of this reactant and this reactant and this product are this, what is the equilibrium constant? You got to do the math. Guess what? Other than when I was a freshman in college, I've never done it. We don't do that, at least in branch chemistry I'm in. So I'm not going to ask you to do that. And to make it a level even harder, instead of giving you moles per liter, instructor will give you, if you have so many grams per milliliters of this, that, and that, you got to convert grams to moles, put it in there, do the form. There's more important things I would like you to learn and practice. But does that answer your question, Ann?
It does. Thank you so much.
You're welcome. All questions are good questions, always. All right, let's get back to the one we were looking at. And the question is, what happens to NO2 and water when you add more ammonia? And if we look at this at equilibrium, there was a certain amount of NO2, certain amount of hydrogen, certain amount of ammonia, NH3, and a certain amount of water. Now in B, we've added more ammonia. And now the equilibrium says, oh no, there's too much ammonia. We've got to get rid of some of it. That's the stress it's under. How does it relieve the stress? It reacts with the water to go this direction. And that means ammonia is consumed, there's less, which it wants to, and water is consumed. Therefore, when something is consumed, we have less water. Now, when the ammonia and the water react, it goes to this side. And we make more NO2 and hydrogen. When you make more of something, the amount you have increases. Now, let's look at number 10. And notice, oh, look, someone was nice enough to write on there for an ice bath. What happens when you put something in an ice bath? It removes heat. And this is something you got to remember. I don't think I have it on important information. And when you put it in boiling water, you add heat. And if you look here, I didn't even give the answer. Oh no, I'm sorry, I left the blank here. All right, so if we have this reaction, by the way, C6H6 is called benzene. I'm an organic chemist, so I know these things. And this is called cyclohexane. And it's the equilibrium. And this is what kind of reaction? Oh, I'm going to make you think. You have two choices, endothermic or exothermic. 5 seconds, go. Bonus time. Time's up. Put down your pens and pencils, hand in your I'm practicing. But anyways, it's exothermic. How do you know that? The heat is on the product or right side. Now, at equilibrium, there's a certain amount of benzene, hydrogen, cyclohexane, and heat. And if we put it in an ice bath, what does an ice bath do? It removes heat. And now the equilibrium says, oh no, we don't have enough heat. We need more heat. How does it make more heat? Benzene and hydrogen react to make more cyclohexane and more heat. If benzene, C6H6, reacts, it's consumed. And when something is consumed, the amount you have decreases. At the same time, to make more heat, you're making more cyclohexane, C6H12, and then when you make more of something, the amount you have increases. Now, let's look at B. Put the same reaction in boiling water. And what happens when you put something in boiling water? You add heat. So at equilibrium, there's a certain amount of benzene, C6H6, hydrogen, H2, cyclohexane, C6H12, and heat. Now you've added heat, and the equilibrium says, oh no, I have too much heat. I'm under stress. I got to get rid of some of this excess heat. How does it do that? The heat reacts with C6H12, cyclohexane, to make benzene and hydrogen. So if we look at putting it in boiling water, when the C6H12 reacts with heat, it's consumed. When something is consumed or reacts, you have less of it. You're going to make hydrogen and benzene because the equilibrium shifts or goes in that direction. And when you make more of something, guess what? You have more and the amount increases. And that's how you do that. And I gave you another one here, but let's do something different. Everybody see the reaction on there? Equilibrium reaction. And Why don't you try this one? What happens to the concentration of A and D if I got an extra I there. Hold on. If I put the reaction in an ice bath. Your turn. And when you're done, give me a thumbs up. And for those of you who are using Symbolis, because your webcam isn't on, give me a thumbs up. I didn't turn off the emoji, did I, for you people? Or are you still working? Let's find out the hard way. All right, let's get going. Now, when you put it in an ice bath, it removes heat. And therefore, at equilibrium, there's a certain amount of heat, A, B, C, and D. And now we've removed heat and equilibrium is under stress. Why? Oh no, I don't have enough heat. Somebody removed some from me. The ice bath did. Therefore, it wants more heat. How can you make more heat? The equilibrium shifts that way. C and D react to make more heat, A and B. If C and D react, what happens to the concentration of D? Well, when it reacts, it's consumed and it decreases. And when C and D react to make more heat, it's also going to make more A and B. And when you make more of something, what happens to the concentration? In this case, A, it will increase. And time again for you to try one. What happens to the concentration of A and D if you put the reaction in boiling water? And I'm going to help you out just in case you forgot. Oh, too small, too big. And this should help you out. Boiling water adds heat. And when you're done, give me a thumbs up or not not to discriminate against the other digits on your hand, you can raise that other digit. Maybe not the middle finger. Oh, I crack myself up sometimes. All right, I think everybody's done. Let's do this. All right, at equilibrium, there was a certain amount of heat, a certain amount of A and B, and C and D. By putting it in boiling water, what do? We add heat. And at equilibrium, there was a certain amount of heat. And now the equilibrium says, oh no, we have too much heat. We've got to get rid of this excess heat. And how does it do that? It reacts with A and B to make more C and D. Because when A and B react with heat, the excess heat is consumed, and so is A and B. Now, if A is consumed, when something is consumed, you have less of it. So the amount you have will decrease. And now, when heat reacts with A and B, it makes more C and D. If you make more of something like D, the amount you have when you make more of it will increase. And let me erase A so I can have more room for C. What happens to the concentration of A and D if I remove some B? Your turn. Oh, it warms my heart to see everybody working on the Chatelier's principle problem. Thank you. I can even see those of you without your webcam are working on it. Thank you. Didn't know I had internet x-ray eyes. I don't. And remember, if you have any questions about this, see me after lab today and I'll help out. Because that makes Dr. White happy to help students, seriously. All right, anybody need more time? All right, let's do it. At equilibrium, first of all, let me clean this up. Oh no, A disappeared. At equilibrium, there was a certain amount of A, heat A, and B, C, and D. If we remove some B, what's the stress? Well, there should be a certain amount of B. Now there's less. Oh no, we don't have enough B. So you need to make more B to replace what you remove. How do you do that? C and D react to make more A, B, and heat because we're replacing what we remove. Therefore, if C and D react, when something reacts, it's consumed. And when something is consumed, that's a D, you have less. The amount you have decreases. And to replace the B we took out, we make more B going this way, but we also make more A in heat. If you make more of something, the amount you have increases. Will increase, and that's how you do it. Now, you might be saying, why am I learning this stuff? Well, I've used in one company, we took phenol plus formaldehyde, and this is an equilibrium to make what's called a resin. That's a fancy name for glue, and water. And to make this shift this way, to make the resin, we first of all added a catalyst, but this was a super slow reaction. And when you were making water, we'd remove it. And that helped shift this to this side and make it go quicker. And that's how we made the resin. Now the resin, hold on one second. Let me see if I can find something. Ah. Now the resin was used to hold glue stuff together. What? Sand. This is called a dog bone. This is sand with the resin. That's why it's black. And this is used to test it. You could put it in what's called an instron to measure how strong it holds the sand together. It's called stencil strength. And what do they use this for? To make your molds for your car engines. Also, next time you're walking along the street and you see the sewer covers, those are made making a mold using sand and a resin. And with that, it's time for our break. Come back in 5 minutes and we'll start with I'll start with, are there any questions? And then we'll do the lab. I'll see you in 5.
Okay, this is the video where we're going.
Be with you in a second. Yeah, same one. Time to come back. Did you ever play hide and seek when I was a kid? What we used to say, come out, wherever you are. God, that's a memory I haven't thought about in ages and ages. How many of you used to play hide and seek when you were a kid? That was a fun game. All right. First of all, before I proceed, are there any questions about anything to do with equilibrium chapter? All right, if you don't feel comfortable asking questions now, remember, I'm going to stick around for a little while after the lab and I'll answer any questions. Also, don't forget, on Monday and Wednesday nights, I have my office hour. By the way, we had a good crowd last night. All right, let's talk about today's lab. And today's lab is food chemistry, or doing chemistry with food. Thumbs up, people. Do you see it on your screen? Thank you. And if you've looked at it, if not, I'll read some of it. All the items that you find in your kitchen or supermarket to put in your kitchen are chemicals. Yes, chemicals. And the food you eat and the ingredients that you use and the ingredients that you use to make various food dishes are composed of atoms and molecules. And the chemistry that you've learned in my class can be applied to food items in your kitchen, such as show and tell, ketchup, or as I like even better, this is good stuff, Sweet Baby Ray's, the honey barbecue sauce. If you haven't tried that out, you're missing something in life. But anyways, the stuff in here is chemicals. If you look at the back here, there's an ingredients label. And this one says tomato concentrate, and then distilled vinegar, and then cane sugar, salt, and other stuff. And if we look at this one, it starts out with high fructose corn syrup. High fructose corn syrup just means sugars. And then distilled vinegar. The ketchup and barbecue sauce both have distilled vinegar. What's distilled vinegar? It's a mixture of water and a compound called acetic acid. And acetic acid is an acid. And in this lab, you'll be investigating the acidity and basicity, meaning is something an acid or base, of various foods and cooking ingredients. Remember, an acid is a proton donor, a base is a proton acceptor. Now, how do we determine this? We measure the pH. which I'll talk more about on Monday, but we started talking, I'll do a little now too. And oops, let's do something real quick. That's better. Oh, I missed it here too. If the hydronium ion concentration is greater than hydroxide, it's acidic, meaning there's an acid present. If hydroxide is greater than hydronium, it's a basic solution. Now, instead of using concentrations, we use pH. And pH is defined as minus the log of the hydronium concentration. If the pH of a solution is less than 7, then the solution is acidic. If it's greater than 7, it's basic. If it's equal to 7, I don't have here, it's neutral. Now, this is something I'll go over again Monday, because I think this is probably the most important thing I'll teach you. Does everybody see my whiteboard? Thank you. Now, what you should know is the pH scale. It goes 0 to 14, never less than 0, more than 14. And the pH scale goes from 0 to 14. When you're at pH 7, that's called neutral pH or neutral solution. When you're below 7, it's acidic. And when it's above 7, it's basic solution. And that's the pH scale. Hold on, I'll give you a second to copy that down if you were. All right, everybody got that down who wanted to get it down? Now, the way we're going to be, if you were in the lab today, there's different ways of measuring pH. One is with a pH meter, which uses a probe, which we won't use. We'll use pH paper. And pH paper is a paper that's been treated that changes color when it's exposed to different pHs. And you have, when you buy the pH paper, a scale, color scale on the box or the container of the pH paper, and you compare the color of the paper to the color of the pH paper. And now I'm going to play a little video for you from YouTube. I think everything's on YouTube except my high school graduation. Maybe when I was born too. I don't think that's on YouTube. All right, does everybody see the white thing with the colors on it from YouTube on your screen now?
Okay, this is the video where we're going to be testing various solutions with pH paper. So you can write down a chart, give it this heading or title, testing pH with pH paper. We've got sodium hydroxide base, hydrochloric acid, vinegar, baking soda, lemon juice, window cleaner, Drano, and detergent. Don't worry about that last row. We actually don't have an unknown. So we're just going to test 8 items. Okay, they're in the same position on the spot plate as they were in the chart. We're going to use pH paper like this. It'll change color, and we'll match up the color change with what we see on this color chart here to try to determine exactly what the pH actually is. So let's do the first one, sodium hydroxide base. And when we compare it, we can see here, yeah, that's kind of a 12. Next one is hydrochloric acid. And we got a nice pink to red color. So that's, you know, pH 1, probably, yeah. The next one is vinegar. And we get kind of an orange color for this one. That's kind of a 3. We've got baking soda. And we got a nice green color being produced there. And that's kind of a pH of 8. Lemon juice. And we get kind of like a pH of 3. It might be somewhere between 3 and 4. Window cleaner, which is ammonia. We get kind of a light green color here. It's around pH of 7, but not quite as yellow as what you would see right there. So somewhere between 7 and 8. Then we have Drano, and we get a really dark blue color there. So that's a strong base, pH of 12. And then we get detergent, and that's kind of like a pH of, well, it's not quite 9, not quite 10, somewhere between 9 and 10.
All right. Remember, when you're above pH 7, it's basic, and below it's acidic. And if you remember, the drain cleaner was dark blue, pH about 12 or 13. That makes it basic. The vinegar was about a pH 3, which makes it acidic. And that's how you use pH paper. By the way, a pH meter is much more sensitive and gives better, but for this lab, it works fine, pH paper. Now, let's take a look at an important thing. In this lab, you'll be reacting acidic foods, those with pH less than 7, with basic food ingredients and other things too. And you'll determine the effect of these reactions on the pH of the food being reacted. This is called the neutralization reaction. When you react an acid, HA, with a base, it reacts in equilibrium, but let's assume it's a strong acid or base, and the equilibrium shifts mainly to that direction. And what happens is you get this and this, which is really together a salt. And what happens is when you react acid with a base, if you have something that's acidic, when you react an acid with a base, you're removing some of the acid. It's called neutralizing it because it moves the pH up. And therefore, you're getting closer to neutral pH, which is 7. And that's why this is called the neutralization reaction. And in this lab, you'll be reacting various foods with 2 different bases and seeing what happens to the pH. Now, the first thing is, let's look at the pH of water. Now, most people think of the pH of water as being 7, and it should if you have ultra pure water. And none of us have that. None of us. Now, in a lab, to take out the ions that are always in water, how many of you have heard of hard or soft water? And that's because there are ions in there. You have filters, and at COD, we have filters that we have a special tap by each sink that's curved instead of, and with one knob only, instead of hot and cold, we have those too. And that gives out deionized water. And one of the things to show students, well, water isn't always, unless it's ultra pure, pH 7. I have them measure it. And it turns out, if I can get to the right screen, the pH of the water in COD labs is about pH 6.7. And I give that to you. If we were in the lab, you'd measure that. Now, interesting story. First, I'm out of tea. Switch to water. Hold on. This pH stuff is thirsty stuff. And one company, I was given a problem to solve, even though it wasn't in my area, but I already had a reputation for solving problems nobody else could. And the company I worked for had a plant in Milwaukee making a certain product for GM, and they wanted to close down that plant. And they were switching the production of that product and other products to a plant they had in Toledo, Ohio. And therefore, we had to close the plant. Well, GM said, unless you can make that perfectly in the new plant, the other plant, don't shut down the old one. Well, I was in charge of that area. And after about 5 months, costing the company $100,000 a month because they couldn't close that plant, the research director called me into his office and said, we got a problem at this coating plant. And I said, I don't work with coatings. He said, well, I want you to solve the problem anyways. And he called in my boss, who was responsible, the assistant vice of research director, which this caused problems between him and me afterward, because he was upset that I was being brought in to solve a problem he couldn't. And he was really upset and took it out on me, or tried to at times. But anyways, that's another story I won't tell. But anyways, here's an interesting thing. We had a product that you could make at one plant, and the other plant you couldn't. And here's where you use common sense. By the way, I was taught by one of the great mentors I ever had, common sense is not common. And here they'd been mucking around for almost 6 months. And I got in and I said, all right, you can make it here, you can make it, you can't make it there. Something has to be different. So the first thing I did was, because water was important, I had them measure the pH of the water in Milwaukee plant. And it was about 7. In Toledo, the pH was, this was amazing, 8.5. And that was part of the problem. The other one was whoever wrote the procedure to make this did a bad job writing it. And they said, use warm water. Well, what did I do? When they were making it in Milwaukee, when they were putting the water in, put some water in this bucket, took a thermometer, stuck it in. It was about 80 degrees Fahrenheit, or I forgot, 27 degrees Celsius. I went to Toledo and watched them, took a bucket. The plant manager was trying to save money, so he didn't warm up the water. It was about 20 degrees C, or about, I don't know, 55, 60. I said, no, let's get it to the same temperature. He said, I don't want to spend the money. I had to call up the research director, who called up the vice president of production, who called up the plant manager and said, do what Dr. White wants, or otherwise you won't have a job. And they did. And by making sure whatever you did here, you do there, guess what? You could do it. Why they didn't do that and played around for almost 6 months, wasted over $500,000, the company money, you'll never know. But anyways, pH of water changes wherever you are. Now that you know that, let's look at the reaction. Now, in today's lab, the first part, you're going to be reacting various food things with sodium bicarbonate, baking powder, NaHCO3. And the reaction, which I don't give you here, I'll talk more about it. We have an acid plus sodium bicarbonate, and you do this in water. It's an equilibrium, but it's mostly to the right. You'll get this plus Na plus, well, let me rewrite this. you'll get a salt plus water plus carbon dioxide given off as a gas. This arrow tells you it's given off as a gas, and that breaks down. And let's look at a video of this. And when you react vinegar, which is an acid, with baking powder, and by the way, in the lab, I have these links. And don't try this at home. All right, everybody see the YouTube on your screen?
Okay, take number 3. This time, we've got a mixture of 1 cup vinegar to 1 cup warm water in a 2-litre drinks bottle with our launchpad system here. This time we're putting the baking soda inside a pop sock that's made out of tipes. Now hopefully that will mean that the vinegar can get inside the pop sock more easily and it won't get wedged in the end of the bottle when it's about to go off, which should mean the gas gets out more easily. Here we go then. So cut a little hole in the pop sock there. We're drying out, we should be able to reuse this actually. Very gently, make sure the inside is dry. We're going to feed our bicarb in the pop sock through the gap. Once we've got bit in, we should just be able to gently dip it in through, push it on down. Right, now we've got the interesting bits. So, put the bottom in the right place, ready to run back very quickly. Launch pads ready with the cork. Here we go, and oh, it actually suspends it. That's a nice feature. Ready? 3, 2, 1. Over we go. Bubbling away nicely. Pop sock looks like it's turned into a balloon. Oh, that's definitely better delivery methods. Look at it go. Oh, that's very frothy. That's very frothy. Whoa! Oh, success!
It's the pop sock.
Right, pop socks forever. Wow.
Do I get the credit for that?
I think you definitely get credit for that. There you go, folks. Stay tuned for the next video. I'll show you how to make one of those.
Jordan, come over here, come over here. This is freaking crazy. You see this house right here?
Yeah, I see it.
Someone is making $50,000 per month. Someone who lives in that house. How do you know that?
Hold on. By the way, that's cool. And
Big thanks to Arm & Hammer Baking Soda for sponsoring this video. Same thing.
sorry about that. For those of you who just had your ears blasted out. But anyways, if you want, and be very careful and do this in a sink, take some vinegar, put it in a container, not in a closed container, and also put a little baking powder. And I think some of you with kids have already done this already. And enjoy a chemical reaction. Now, coming attraction. Monday, I'll tell you about how Dr. White did this when I was 5 years old, because my father taught me something, but you got to wait till Monday. Sorry about that, but you do. All right, let's go back to the lab. And what you'll do is you'll put about 10 milliliters of DI water and about 1 gram of the food item in a beaker. Use a beaker instead of test tubes because it's easier to clean out later on. And then you'll mix it. Then you'll test it with the pH paper. Then you'll add a little bit of baking powder, mix it, check the pH, add a little more, and then add a lot more. And the products you will be testing are, oops, this got mixed up somehow. I don't think we do orange juice. Vinegar, ketchup, tomato paste, lemon juice, mustard, and Coca-Cola. Oh, there is orange juice in there. I messed up on that table. And I have, if we were in the lab, you'd observe it, see bubbles. And first, the initial pH After you add a little sodium bicarbonate, a little more, and a lot more, and you see what happens to the pH of various things. Now, the second part will be using another base, sodium hydroxide, and now you'll do the same thing. By the way, the solution you'll use is a 0.1 capital M NaOH solution. And now you know what that means. It's 0.100 moles of NaOH per 1,000 milliliters. And what you'll do is the same thing. Add some water in a beaker, some of the food, measure the pH, add about 2 drops of sodium hydroxide solution, measure the pH, add 2 more drops, measure the pH, and then add a lot more, 10, and measure the pH. And here I have orange juice in the right place, and you'll be measuring, doing this with vinegar, orange juice, ketchup, tomato paste, lemon juice, and mustard and Coke. And here's the data. Notice it stays clear because you're not making any gas. I should point out right here, the general reaction you're doing and it's an equilibrium, but it's mostly to the right. You make a salt plus water. No CO2 is formed here. And you measure the different pHs, which I show you. Like for vinegar, it starts out at pH 1. You add some of the sodium hydroxide, it's pH 5, then 7, then add a lot more, it's 13, which is pretty strong base at that point. Remember, the pH scale goes from 0 to 14. And then, guess what? I have some questions. Oh no, look, the thing students hate the most, please include an explanation for your answer. By the way, these answers don't have to be 1,000 words, just a brief explanation. And that's today's lab. And now you find out, wow, these are really chemicals. I like this, but this is my favorite. If you haven't tried this, oh, I wonder if I can get money. You know, in the movies, they do product placement. I wonder if I can get money from these companies. No, I'm not going to hold my breath. And with that, I'm done. That's today's lab. That's today's going through the problem set. Hopefully you had a fun morning with Dr. White. I'm going to say goodbye. I'll see you people on Monday. Don't forget to study. Test number 4 is coming up soon. And don't forget to, if you want to, and I'd recommend you do, work on your extra credit project, get it to me. And with that, I'm going to stick around after lab if anybody has any last minute questions. But with that, I'm going to say, gang gazoon, goodbye, bye.